Hello. In this video we will be discussing the third of the addition reactions to alkenes. It's called halogenation because all you're adding is the element of bromine or chlorine. That is the X2 in this equation. Could be Br2 or Cl2. Turns out iodine doesn't work because it's not reactive enough and fluorine is too reactive, so we just use Br2 or Cl2. And it's very simple in that both carbons pick up a halogen, so one goes on one carbon and one goes on the other carbon, and of course the double bond disappears. Because both things we're adding are the same as each other, the regiospecificity isn't applicable because you don't have to decide which one goes on which carbon because it's the same thing on both. Notice that I've drawn the two halogens opposite to each other, one up and one down here, because that reminds us that the stereospecificity of this reaction is indeed anti. Not that it always matters, in fact it really doesn't matter at all unless you're on a ring. But even in this formula, I've drawn it that way just to remind us. Okay, so now here are three examples of that reaction. Here is an alkene, in which we're going to add Cl2. The product should have a chlorine here, and a chlorine here, and the double bond should disappear. And we see that that is the case. So a chlorine on here, a chlorine on here. That hydrogen that was there is still there, and so we just get 1,2-dichloro, 2-methylbutane. Here's another example. It's drawn in a stick figure format, but just another alkene. And if we add bromine to this, one of the bromine goes on this carbon, and the other bromine goes on this carbon, and the double bond disappears. So again, we get a dibromo compound. And this one being a ring, it's now going to matter how we show the stereochemistry. So the two bromines add to the double bond disappears, it becomes a single bond. One bromine adds here, one bromine adds here, but notice that the two bromines end up opposite, so one is on a wedge and the other one's on a dotted line, because it's again an anti-addition. Now one thing to notice here, this is the product, but it's an enantiomer, which would have this bromine down and this bromine up. It's not the same thing. It's they are in fact enantiomers, so we're going to write down plus enantiomer. Here's the question, do you have to do that with every chiral molecule? No, because notice in this case, this is a chiral carbon. It's got a hydrogen, a chlorine, a methyl, and this other big group. So why don't we write plus enantiomer in this case, even though both enantiomers do get formed here? Well, the reason is because this kind of diagram doesn't attempt to show stereochemistry. So this diagram itself represents both enantiomers at the same time. This diagram clearly represents one of the two enantiomers, and so you have to put in the little phrase plus enantiomer if they both get formed. Now let's talk about the mechanism. In the first step, the halogen molecule actually comes in on the top of the alkene and forms two bonds at the same time to the two carbons of the alkene. So this bond and this bond both form at the same time, and that's important because it doesn't give the molecule a chance to rotate the double bond in between. And the other halogen from this X2 molecule goes off as X minus, so we end up with a positive halogen and a negative halogen. The positive halogen has two bonds and two lone pairs. The negative halogen, of course, has four lone pairs on it. That's the first step. This kind of molecule is called a halonium ion, or bromonium if it's a bromine, or a chloronium if it's a chlorine. And it's very strange because it's a three-membered ring, which is pretty unstable in itself. Plus it has a positive halogen, and as we know, halogens don't want to be positive, they want to be negative. Nevertheless, this is in fact the intermediate here. So in the next step then, the halonium ion, and notice that there should be a negative charge on this halide. I just left that off by mistake. But what happens is that negative halogen comes in on the bottom and attacks one of these two carbons, forming a bond. So this new bond came from the X minus, breaking this bond. And so this bond still remains. That one between the carbon and the halogen becomes this bond between the carbon and the halogen. That remains. But the other bond that was between the carbon and the other carbon and the halogen is no longer there. So this is not a ring anymore. And the fourth position on this carbon is now taken by the new X. That's this one coming in from the bottom. And so by definition, the two halides have to end up on opposite sides because the X minus has to come in on the bottom of wherever the original halide was. Now, let's look at the first step again in a little bit more detail. Notice what happens is the halogen comes in on top of the flat alkene. Three things happen all at the same time. So this bond goes out of here and forms a new bond between the carbon and the halogen. One of the pairs of electrons from the halogen goes in here and forms a new bond between the carbon and the halogen, the other carbon and the halogen. And this bond that was holding the two halogens together, goes off by itself onto this halide. So it becomes X minus. this becomes X plus because net it's losing one electron. It's losing one from here, gaining one from here, but losing one from here, so it becomes positive, and the double bond is no longer there, and we now have the three-membered ring. And then in the second step, the second halide, the X minus, comes in, forms a bond here, breaks a bond here, and we end up with the dihalide anti, one halogen up and one halogen down. And this explains why the reaction stereospecificity is strictly anti. That's the end of the presentation for today. Thank you for your attention.